Hey physics nerds, this is another edition of Review with your boy Mapoy. That was so lame, guys. I'm sticking with it. Okay, this is the Modern Physics Unit Review. This is our optional quiz. Again, you don't have to take it. It's the end of the year, but if it helps your grade, I'll count it. Alright, let's begin. Enough chitter-chatter. Okay, topics. Wave-particle duality of light, photoelectric effect, electron volt, energy level diagrams, mass energy equivalence. I also forgot to include here antimatter and the fundamental forces. I'm going to abbreviate that as FF. And we start with the dual nature of light. Light acts as both a wave and a particle. We've already talked a lot about the wave nature of light from our previous wave units. And here we start with our photons. These are particles of light. Here we also talk about Young's double slit experiment, which involved diffraction and proved that light also acts as a wave. Okay, then we go on to the photoelectric effect. Here, when you have electromagnetic radiation striking a piece of metal, electrons could be emitted, and these are known now as photoelectrons. So the moment it leaves the atom, that's when it becomes a photoelectron. So here you have some EM radiation striking an electron. Once it gains enough energy to leave the atom, it then becomes a photoelectron. And so this energy in the photons can be quantified using these equations. These are on the reference table. E equals HF, and E is equal to HC over lambda. So typically we go by the frequency, but in case they don't give you frequency, you got to find it through wavelength. Okay, so let's start with this. What is H? That's Planck's constant. This is on the front of the reference table. And H is equal to 6.63 times 10 to the negative 34 joules dot seconds. This you could find on the front of the reference table. This is known as Planck's constant. And with these two equations, you could quantify the energy in the photon. But here we have another unit of energy known as the electron volt. And you'll see when you calculate using E equals HF, you're going to get these numbers with these big negative exponents. Electron volt helps to simplify these numbers. How? You're either going to multiply by this number. So for every electron volt, you have 1.6 times 10 to the negative 19 joules. So electron volts are the unit of energy used on energy level diagrams. So you're going to see later on energy level diagrams, and the energy unit they use is electron volt. Okay, the energy in electron volts cannot be used with the energy equations using Planck's constant. So the ones I showed you on the previous slide, E equals HF, E equals HC over lambda, those have to be converted to joules to use those equations. If you have electron volts, you have to convert it to joules. And how do we do that? Conversion tips. Using this phrase. It's not really a word, but it's helped people before. Measured. It's weird, I know. What does it stand for? Okay. Gotta multiply by the number to go from electron volts to joules. And then going from joules to electron volts, you divide by the same number. Okay, so what I mean by number, I mean this. This is also on the reference table. So if you're going from electron volts to joules, which is what is most common, so you pick a number off the energy level diagram, it's in electron volts, you got to convert it to joules to use those Planck's constant equations. So you're going from electron volts to joules, which is what this MEG part is, you multiply. You multiply going from electron volts to joules, but going from joules to electron volts, you divide, again by this number. So this number goes on the bottom. So you're either multiplying or dividing by this number. And here's our handy dandy energy level diagram right here. And it shows the energy level diagrams for hydrogen and mercury. As I said before, right here, electron volts, EV. So what does this show you? So if you think back to chemistry, what do electrons have to do to get excited? They have to absorb energy, and then they go up to a higher energy level state. And then when they come back down, they release the energy in the form of light. So let's start here. Hydrogen in its ground state. In order to jump up to the higher energy levels, it needs to absorb photons with the exact amount of energy required to make the jump. So how much is that energy? You take the difference. So the energy required to jump to different levels, you need to figure out using this equation. Initial minus final. The energy of the initial level you're going from to minus the final energy level you're going to. Okay. As an example, if you want to go from the first ground state to the second energy level, then you need to take the difference. You're starting from the first energy level, so you're doing negative 13.6 minus a negative 3.4. You have to keep the negatives. So minus the negative, you end up adding that, and you get a negative 10.2 electron volts. So you need exactly 10.2 electron volts to jump from the first energy level to the second energy level. If you go below that or above that, it won't reach the level, it'll just fall back down. So if you have anything less, like 10 electron volts, or anything more, like 11 electron volts, it will not go to the desired energy level. So once again, if you're even going from the sixth to the second, take the difference and you find out just how much energy it needs to go to those levels. Same thing on the mercury energy level diagram. Now if you see right here at the top, ionization, once it consumes all of that energy, it finally leaves the atom. You can actually go above that, because once it goes above, it finally leaves the atom, and it leaves with a lot of speed. The rest become kinetic energy. Then here's mass energy equivalence, where you have a conversion of mass into energy and vice versa. This is ruled by this famous equation right here, E equals mc squared. Yes, Einstein made this equation. Okay, so what does it do? Let's say you have a mass of 1 gram. This also happens to be 0.001 kilograms. You have to keep your units in kilograms, guys. And c is the speed of light in a vacuum. This is on the reference table. 3 times 10 to the 8th meters per second. You got to square it. So let's plug it in. This is an example showing how much energy is converted from 1 gram of mass. This is about, yeah. The energy you get is in joules, so 9 times 10 to the 13th joules. This actually was the amount of energy used in that atomic bomb dropped on Japan. Yep, it only took 1 gram of substance to blow up an entire city. That's how crazy this is. Pause. Oh my god. Okay, then let's talk about antimatter. So if you see anything anti, you just take the opposite sign for the charge. So same mass, opposite charge for those antiparticles, or sometimes different characteristics. Example would be a proton and the antiproton. Okay, the proton has a charge of positive 1e, so the antiproton will have a charge of negative 1e. These would also have the same mass. Same thing with the electron and its positron. Electron would have a negative 1e charge, positron would be positive 1e. Some of you might be thinking, isn't like the antiproton the same as an electron? No, because these two have different masses. Electrons are much smaller than protons. So the opposite of an electron would be the positron, the antiparticle to the electron. Okay, and when you have these two particles colliding, they will annihilate each other and convert its mass into energy in line with this E equals mc squared equation. So you could get a lot of energy from colliding protons and antiprotons together. They annihilate each other and become energy. Yeah. Okay. And then in our universe, we have the 4 fundamental forces. The strong force holds protons and neutrons together in the nucleus. The only particles unaffected by this are leptons, and I'll elaborate on those later. Then you have the electromagnetic force, which is attraction repulsion due to stationary and moving charges. Then you have the weak force, responsible for radioactive beta decay. And you have the gravitational force, which is attraction due to mass. So there are 2 types of matter, hadrons and leptons. Hadrons are affected by all of these. Examples include protons and neutrons. And then there are leptons. They're affected by everything except the strong nuclear force. An example of this would be the electron. Why would it be unaffected by the strong force? Where is the electron located? Outside the nucleus. It doesn't have to worry about the strong force. So this leads us into this last chart you need to know on the reference table. So it's the standard model of particle physics. So basically it classifies all of matter into categories, hadrons and leptons. And then you can break down hadrons into baryons and mesons, which differ in their quark composition. What the heck is a quark? So there are particles actually smaller than the protons, neutrons, and electrons. So yes, there's some things even smaller than our subatomic particles. And these quarks make up the likes of protons and neutrons. So baryons, examples of those are protons and neutrons because they both need 3 quarks to make them up. Then you have some things like mesons which need a quark and an anti-quark. Again, anti meaning you just take the opposite sign. So anti-quark, for example, if we have an up quark, the anti-quark or the anti-up is not down. Anti-up is not equal to down. Anti-up is the same mass, but opposite sign and charge. So an anti-up would have negative 2/3 E. Okay? So, as an example, to prove that a proton is made up of 3 quarks, 2 ups and 1 down, I'll show you right here. So you need to combine 2 ups and 1 down. So you get positive 4/3 E minus 1/3 E. You get positive 3/3 E, which is equal to positive 1 E. And that there is our proton. If you remember, the charge of a proton is positive 1 E, and here we just verify that 2 ups and 1 down make a proton. Neutrons are 2 downs and 1 up. You could do this same method to verify that it comes out to 0 E, which is the charge of a neutron. Okay, so enough about quarks and hadrons. Here, this table shows you the 6 leptons. I know all their names are strange, but physicists are just weird in general. So these are just the names, no real significant meaning. They're just names for these quarks and leptons. Okay, and that's the end of this video, and pretty much the whole year of Regents Physics. Good luck, guys, on that modern physics quiz. Again, it's optional, don't have to take it, but it doesn't hurt to try. Good luck, guys.